In the last video session, we discussed the effect of process non-idealities and variability in the voltage and temperature operating conditions, which actually introduces variability in the performance, specifically the delay of logic gates in a VLSI digital system. And this is given a fixed design, just one design that has been that you fabricated multiple dies. This variability in delay due to process, voltage, and temperature would cause a spread, a variation in delay between die to die or within the same die, between transistors within the same die. We had discussed at some length the effect of process non-idealities, and in this session we will continue the discussion with an elaboration on the source of the voltage and temperature variabilities. But first, let us try to quantify the amount of variability in current due to variations in threshold voltage and transistor length. As we've discussed in the last session, variations in the process can actually lead to some variations in the geometrical lengths, the geometrical distances, and changes in the dopant profile, and also the geometrical properties will also change the electrical property, which is the threshold voltage. VTH and L variability are typically most studied because these tend to have the most significant effect on variations in speed. So here it's a simple study looking at the trying to quantify the change in on current as well as off current of a MOSFET device. So an on current is when the device is turned on. There's a logic 1 applied at the input, and the device is conducting. And the off current is when the channel is not formed and the device is supposed to be non-conducting, but there is a small sub-threshold current that still flows between drain to source, and this current is associated with no useful work because it does not actually charge or discharge capacitance at the logic gate output. It's just wasted power. So here you can see the square law relationship between current and gate voltage and gate voltage here and threshold voltage here, except that we've seen in the past lectures that this due to short channel effects, this is no longer a square law, that is alpha is no longer equals to 2, but it's something closer to maybe 1.6, 1.2 to 1.6 due to short channel effects. So as we minimize the technology, the transistor gate lengths, this mobility saturation, velocity saturation, reduces the effect of the gate voltage on increasing the current. And the off current, that is the non-conducting subthreshold current, it has an exponential behavior because it's very similar to a bipolar junction transistor structure, where the actual value of the current depends on the threshold voltage here, and is nothing else but a capacitive divider between the gate and the channel, as explained in previous lectures, and this value is in between roughly about 1.5 to 2 in modern devices. And VTH is the Boltzmann thermal voltage, approximately 26 millivolts. If we take sensitivity analysis of these equations, that is, we differentiate the current with respect to change in length, dl, and change in threshold voltage, we get an expression for the on current and off current. The amount of the new on current and new off current for a given deviation of the transistor length, gate length, and a given deviation on the transistor threshold voltage. Alternatively, if you take this nominal current, that is the design current, as the denominator here, then this term actually tells you the fraction of change, the proportion of change for a given delta L or a given delta V threshold, what is the fraction of change in the on current? You can observe that the on current will change linearly with the fraction of change in dL and dVt. But what I'd like to draw your attention to is the percentage of change in on current due to dL and dVt is dependent on the ratio of dL over L and dVt over VDD over VT. Okay, what this means is that when we go to in terms of fabrication technology, the variation in transistor channel length, it's sort of set by the resolution limits of your lithographic system. So it could be a couple of nanometers to a couple of 10 nanometers, right? But what makes this effect more serious is that we have actually moved L, we've changed it from maybe 1 micron, that is like 1,000 times more than a nanometer, to something like 10 nanometers. So in the older process technologies, which larger L, like in order of a micron, the delta L is actually a really, very small fraction, like 0.1% of the actual length. So you don't see much change in the on and off current due to the geometry variability. But because we've shrunk the transistor so small now to about 10 to 12 nanometers, the variability due to the lithographic inaccuracies are on the order of 10 to 20% of the actual transistor length. And the same thing also applies for the threshold voltage. Threshold voltage could, typical threshold voltage variations are order of like tens of millivolts, 10 to 20 to 30 millivolt kind of variations. In the old days when ICs were run at 5 volts VDD, so 20 millivolt probably represents about 2 to 5% of the entire VDD minus V threshold. But today, as we try to scale down VDD to about 1 volt, 20 millivolt is quite significant. It represents probably about 22 to 3% already of the voltage headroom, like VDD minus VTH. So it is the miniaturization of transistors that actually cause the variability in on current to become more significant. But although on current varies by now maybe like between 20+% depending on delta L to about like 2 to 3% depending on dVTH, it is the off current, the subthreshold leakage current, that sees the largest variation, right? Because here, of course, you still have that same 20 to 30% due to delta L over L, but the change in threshold voltage is now on the order of the thermal voltage, which is about 26 millivolts. So we're seeing a factor of almost 100% here. So the off current is where we expect the greatest changes or switch in variability due to variability in threshold voltage. So the variability in threshold voltage is really a serious problem in low energy integrated circuits. Okay, let's move on. So let's talk a little bit more about the issue of voltage variability. That is a variability in operating conditions that leads to a change or variability in delay. Where does this variability arise? So I'd like to draw your attention to this graph. Okay, there are 3 kinds of variations, and this voltage variation actually arises during the switching activity of the transistor. So let's say your logic gate is going from a high to a low, and then a low to a high, and this happens in a very, very short time instance, a very short dt here. And so the on-chip capacitance and the inductance due to the package, that is the connection, the wire bonds to the leads. This introduces additional inductance, this introduces additional resistance. And as we are miniaturizing the size of integrated circuits, the relative size of the wire bond, the package leads, the relative size of the on-chip capacitors, the decoupling capacitors becomes much larger than the actual interconnect, the actual metal wires between transistors. And so the parasitic resistance and inductances of these connections are relatively large. And so any large changes in voltage, so from L di dt, okay, this is the inductive changes, will lead to huge swings in voltage. And what happens is this large swings in inductive and resistive parasitic voltage drops cause a significant droop in the voltage supply to transistors. And of course, if you've studied the noise margin of digital logic gates, if the voltage headroom drops below a certain amount, then this introduces noise and may actually cause problems, trouble to the cause a corruption of the digital values. But here we're more concerned with the fact that the headroom decreases not enough to compromise the noise margin, but it will actually definitely change the transistor switching speed, because the VDD, the effective VDD actually momentarily drops due to this parasitic drop, and of course this reduces the available on current of the transistor. So that is this major drop here. As you can see, the first droop, which is a change in voltage, a very short transient change in the voltage on the order of nanoseconds due to the on-chip, the parasitic inductance of the wire bond, the packaging, as well as the long large metal layers that connect to these pins. And then there's a second droop, smaller droop, voltage droop on the order of about 5 to 10%. This is actually due to the parasitic inductance and resistance on the electronic board. That is the connections on the PCB to the chip package, and the coupling capacitors help to mitigate some of these issues. So voltage variability arises from the packaging parasitics, because we have now miniaturized the integrated circuit so much, and these packaging parasitics cannot be ignored, because the switching frequency of the logic gates are so high that it causes large droops in the voltage for very, very short transient times, 1 nanosecond, but this droop is enough to affect, because the magnitude is so large, is enough to affect the drive current and hence the switching speed of the MOS devices, the MOSFET CMOS gates. Next, let's talk a little bit more about where the temperature, the variability in speed due to temperature differences happen. We all know that in a modern VLSI IC design, right? So it's something like this. Like this graph actually shows a heat map of the design with maybe the cache region laid out here, and this is actually the core. The core would be like maybe like in a microprocessor is the arithmetic logic unit portion, and you can see that at certain parts of the logic, that it's really high rate, so meaning the temperature is like really high. Here it's probably exceeding about 100 degrees. It's about 120 degrees, whereas in other parts of the chip, let's say like for example the cache or with static RAM, where the excesses aren't so high, there's not as much switching, the heat dissipation is lower. Okay, so in a typical VLSI digital systems, there are hotspots on the chip, and these hotspots create large temperature gradients, and these hotspots can change, the profile of the hotspots can change on the order of milliseconds. So in regions where the temperature is higher, the speed of actually switching the interconnect, the wire, actually reduces, and high temperature also reduces the threshold voltage as well as the carrier mobility. And we would actually say that it also increases the leakage current as well as the aging. We'll discuss that a little bit later. But I'd first like to draw your attention to this graph here. So as you can see, as a function of supply voltage, the speed as a function of supply voltage. So the delay, of course, is minimum at a higher supply voltage, because we're applying more voltage, we have more current, and more current means that we can actually charge and discharge the logic gates quicker. So as the supply voltage reduces, of course, the delay increases proportionately. What is interesting is that at high supply voltages, a higher temperature leads to a greater delay. But at low supply voltages, a higher temperature actually leads to a faster operation on the chip, as opposed to a lower temperature. And let's try to explain this inverse temperature dependence, because there seems to be a sweet spot of temperature of supply voltage where the behavior of high or low temperature actually inversely changes the speed relationship. Okay, let's first consider the case of a high supply voltage. Um, at high temperatures, there's a dual effect. There is a reduction of the threshold voltage, which means that for a smaller voltage change, of course, there's more current, and there's also a reduction in the carrier mobility. But at high supply voltages, the carrier mobility is actually the dominant effect, because the supply voltage is actually so high that any changes in the VTH does not significantly affect the change in the current, the driving current, and remember, the driving current is what determines the propagation delay, the speed of switching of the gate. So at high supply voltages, the temperature effect on VTH is not significant enough, and it's actually the degradation, the reduction in carrier mobility that dominates, and that's why at high supply voltages, the higher temperature actually leads to a reduced speed or an increased delay in transistor switching. Whereas in the case of the low supply voltage, now we're talking about a lower headroom, changes in the threshold voltage now become significant, because at a lower supply voltage, if you actually reduce the VTH a bit more, the increase in current due to the lower VTH would actually outpace the decrease in carrier mobility, and this is what you are seeing in this situation here. Okay, so bear in mind that the temperature gradients across a single die would actually lead to differences in speed performance, and that differences in speed performance is further nuanced by whether you're operating at a higher voltage supply or a lower voltage supply, and these variations in due to temperature variability can change on the order of milliseconds, depending on the activity patterns of the computations in the VLSI circuit. And I'd just like to highlight that nowadays dark silicon is already becoming a trend. And what is dark silicon is actually this trend that the industry thought leaders observed, that most of the in an IC in a complete die, the majority of the circuits within the die are actually switched off, turned off. That means no power is allowed to flow for an extended period of time. So this renders them dark or unpowered, and this is becoming a trend to operate most ICs now, that you're actually operating like maybe 50 to 70% of the chip is now powered down, not powered, to avoid the leakage current and to reduce the heating associated with them. Because again, heating increases the leakage current, which is power loss to no useful work, and it also increases the severity of the aging problem, which we will discuss next, which is a problem of reliability. Okay, the next concept I'd like to cover is you've seen that process voltage and temperature variations affect the delay of individual gates and transistors within a die, and of course between dies. But it also affects the total energy consumption, as we've mentioned many times. This idea of the sub-threshold current being changing so much, with so much variance due to the change in the variability in threshold voltage. So if you plot the normalized on current, that is the current when the transistor is conducting, and the normalized off current, the sub-threshold leakage current, you find that the spread of normalized on current is like 20 to 30%, but the normalized off current varies at least 6 times to about 20 times. Okay, and if we try to quantify what is the average leakage current in a circuit, right? Because of course, if you have a more detailed circuit model, you can actually model statistically the average the threshold current across the whole circuit. But if you wanted a quick estimate to see what would be the average power leakage power consumption, you can actually try to estimate the average sub-threshold off current. So we know that I off is proportional to this factor here, e to the power of VTH, and threshold voltage, divided by N, that's a factor of between 1.5 to 2, that's the capacitive voltage divided at the transistor gate, and VT, the Boltzmann terminal voltage, roughly about 26 millivolts. And in a given integrated circuit, the threshold voltage can be modeled as a random, normal random variable with a mean mu and a standard deviation of sigma. And of course, this variability arises from all the geometric dimensional variabilities, the channel length, the channel width, the dopant profile variability due to the process variations. And I of, because of this relationship, follows what we call a log normal distribution. And in a log normal distribution, the mean value of I of is given by this term here. So the important point to note here is, of course, this gives you the typical anticipated thermal voltage if you the anticipated leakage current if you are not considering any of the variability. But the key point I'd like to draw to your attention is that the anticipated average leakage subthreshold current is dependent largely on the variance of the VTH. So if you actually have a process that has a large variance in VTH, the mean subthreshold current goes up significantly, in fact by an exponential power. Okay, so this equation gives you a very handy estimate of the average subthreshold leakage current and this is influenced by the subthreshold voltage variability. In the final set of two slides, I like to discuss the variations in transistor performance due to the phenomena of aging. So this is less of a variability problem, but it's more of a reliability problem. But with reducing transistor size, it also is becoming a variability problem. So it is first a reliability problem, meaning that over time, the same die's performance will change, and transistors across the die themselves over time will be more and more different because of the aging mechanism. And what is an aging mechanism? It's really a degradation of the transistors that affect the speed. Why does this arise? Because in modern transistors, the gate oxide thickness, that is the dielectric silicon dioxide, the thickness of silicon dioxide layer separating the metallic or the conductive polysilicon or metal gate with the transistor channel. Okay, so the thickness of this is on the order of 1.5 nanometers. And we've sort of scaled down the voltage from, let's say, about 5 volts to now about 1 volt, but we've scaled down the thickness of the oxide even more, right? It's on the order of like a factor of 1,000 or more. So this causes much higher electric fields operating between the gate and the channel. That means the electric fields that has developed over the oxide thickness. And under these high electric fields, this non-conductive dielectric silicon dioxide, the lattice structure of this actually breaks down. It actually degrades. There are sort of like defects that get created in the dielectric where charge, the free electrons or holes can actually be created within the dielectric. And what happens over time is more and more of these trapped charges appear in the dielectric and they start affecting or changing the threshold voltage of the transistor. And of course, as you can understand now, changing the threshold voltage changes the on current and as well as the leakage current, and it also changes the speed as well as the energy consumption of the device because it changes the leakage threshold current. And the three main mechanisms by which this degradation of the oxide occurs. If it is due to the gate to channel, the high electric field of the gate to channel, this is known as the negative bias temperature instability, NBTI. NBTI affects PMOS devices, and positive bias temperature instability affects NMOS devices. So this is the creation of charges that get trapped in the dielectric due to the gate to channel electric field. If the charges are trapped in the dielectric due to the drain to source electric field. Again, this is also something that is getting worse and worse because the voltage is not scaling down as fast as the channel length. So the electric fields from drain to source also are increasing. Then this is known as the hot carrier injection. It is still a very similar degradation mechanism. That is the electric, the free charges are trapped and they are disrupting the lattice structure of the dielectric within the gate oxide, the gate oxide, the silicon oxide. But the source of this, the origin of this, is actually the drain to source field rather than the gate to channel field, which is due to NBTI. And there is a third mechanism for this oxide degradation. It's called the time-dependent dielectric breakdown. It is the existence of the free charges within the dielectric, and then when you start applying a electric field, and the electric field is typically quite non-uniform because of all the various channel and gate engineering, this leads to the charges actually creating a conductive path within the dielectric, and this causes the TDDB mode of breakdown. So the goal of this slide is just for you to have a general understanding that there are these three major breakdown mechanisms due to three different sources of electric fields or physical mechanisms, but really it's the problem of charge getting trapped in the dielectric, a very thin dielectric layer in the transistors due to high electric fields. And out of these three effects, NBTI and PBTI increases the transistor variability over lifetime. That means if I give you a given die, and let's say you have like a million transistors on it, NBTI will cause a greater variation over time as you keep operating, as you keep running this particular die, as you keep switching it, as you keep computing jobs on this die. Over time, the performance of the transistors, the million transistors within this die, will have more and more variation due to the NBTI or the PBTI degradation mechanism. So aging does induce more variability. It would actually change the entire die's performance over time, and this would be more due to hot carrier injection and TDDB, but it also increase the variability of delay performance between individual transistors, and this is due to NBTI and PBTI. So these aging-induced variations at the transistor or logic gate level. There are also aging-induced degradations of the interconnect, the wires. And the primary mechanism for these aging effects is a phenomenon known as electromigration. So as the wires are always conducting charge, you're applying electric fields, turning off the electric fields, applying electric fields, turning off the electric fields. When you keep the electric fields on, when the wires are actually, the metal layers are actually conducting, because this is now under high electric field conditions, it's the same voltage but the dimensions are low, the velocity and the acceleration of the charges are actually really high. So they hit, and there's momentum transfer between the electrons to the metal ions. So the metal ions of your routes, your interconnects, receive momentum from all the current, and they diffuse and they migrate, and the net result is over time there are small voids, that means empty regions that are created on the metal interconnect. And as you can imagine, this creates all kinds of weird non-uniform electric fields, and it changes the geometry of the interconnect, and that changes the capacitance resistance properties, and this causes changes in the actual digital circuit speed as well as power consumption. And of course, besides the electromigration effect, which is the main one, there's also stress cycling. You change, the circuit operates under changing temperature gradients and very quickly, and then it expands and contracts, so this will create stresses. And also thermal cycling, the heating and cooling of the chip also creates aging effects that perhaps change the profile of the doping due to maybe diffusion effects and all that. So the key point here is to realize that over time the performance of the VLSI die will degrade and will increase in variability due to changes in the transistor performance and changes in the interconnect dimensions. And this reduces the reliability. That is, it reduces the ability of the die to actually give consistent performance over time.